So we just okay. So we have discussed modeling. Modeling. There are two kinds of modeling. What is analytical modeling, and experimental modeling. Experimental modeling. Experimental modeling. Okay. So analytical modeling means using mathematical equations. Like we have taken example. We have taken example of a transformer, where we need to know the what are the components or inside the transformer, what are the equivalent circuit of a transformer, etc. Then based on that we'll model power dissipation, we'll model the efficiency, etc. Okay, so what is experimental modeling? Experimental model is directly taking the transformer out from its position and giving different inputs and seeing the what are the different outputs, and basically and based on that experimental evidence we are trying to model the for example, best example of experimental modeling is you have given a resistance. For example, you are given a resistance, so you're told to model the resistance. So what you'll do, the resistance, most important parameters across the resistance is voltage, how much voltage it is, we can give it across it, how much current it can dissipate, etc. So what we'll do, we just give a variable voltage source across, connect across the resistance, and we try to vary, right? While we are varying, we'll try to measure the current I, right? And we'll try to measure the current using an ammeter. Now what you'll do, now we go on varying the voltage, different voltages, and same time you'll be plotting a graph. But the graph basically it will be I. This is the dependent parameter. Why dependent parameter? Because I'm varying voltage. Voltage is the independent parameter, right? I'm varying the different values of voltage. I'm uh, trying to measure the current. So my independent parameter is V, because based on V, I'm not depending on voltage is not dependent on anything. I'm manually varying the voltage, so it is the independent parameter. So based on the voltage, my current is varying. So current is a dependent parameter. So what I'll get a graph something like this. Okay, so this graph is nothing but inverse of resistance, right? 1 by R, right? You know the slope is tan theta, etc., etc. So this is the experimental kind of modeling. Now after completing the modeling, I know how the resistance is going to behave, all the different points of voltage and current of this resistance. I know the power dissipation V into I know what is maximum current possible, maximum voltage possible, wattage, etc. So this is the experimental modeling, right? So this is we are familiar with. But analytical modeling we'll be discussing mostly here based on a mathematical analysis, right? For fun, the example we took in the last class is transformer. So basically how we model transformer, we know transformer has two input and output, right? We have input and output. We have some kind of coil input, right? Input. Okay, so this is a transformer, and we know there is some input voltage. We'll be applying some input voltage V1, output voltage V2, and there will be current I1 and this output current I2, right? So in the analytical modeling, we represent the system, which can be mechanical system, electrical system, hydraulic system, or any kind of system like pneumatic system based on gases, etc. So system we represent the system using a equivalent circuit or into its minute components, right? For example, this transformer, how we'll start is uh, basically what we want to study. First thing we have discussed last class is, right, purpose. Why we are modeling, the purpose is very important. So, okay, first we have to be clear why we are modeling, that is the purpose of the modeling. Then once the purpose is clear, we should know what are the boundaries. What are the boundaries? For example, here transformer, mostly the purpose of modeling is to find the efficiency. What are the parameters which affects the efficiency of the transformer, right? And this power factor, what are the input power factor, output power factor analysis, right? Frequency analysis, etc., right? To how to improve the efficiency. So you have to measure the losses of the transformer, etc. These are the some of the purpose, right? So here I'm just taking any of the random purpose, for example, losses, to understand the losses of the transformer. Okay. So then I have to postulate a structure. So the transformer I have to model using some circuit elements, right? We have input voltage and current. So definitely the circuit elements will be resistance will be there, which blocks the current. There will be capacitors, there will be inductors, etc. In transformer, definitely there are a lot of winding. So it will be inductor will be there in the input and output. So we try to model the transformer using these elements. We called lumped parameters. Then after we have modeled it, for example, then we will use some already existing theorems like Kirchhoff voltage law, Kirchhoff current law, etc., uh, to complete the mathematical description, right? So all this mathematical description will be utilized in the physical laws. Can be voltage law, KVL, KCL, whatever, right? For the getting the final mathematical equation. For here, uh, in this, everyone knows the working of a transformer. There are winding, N1 winding in the primary, N2 winding in the secondary. Okay, so we know the ratio V1 by V2. V1 by V2 will be equal to N1 by N2, right? This we already know about the trans. It will be I2 by I1, right? These all things we already know. Now, based on this basic idea, if you go deeper into transformer or the machines, you can there's a set of tests we'll do. Some of the tests which we implement on the transformer, or we test the transformer. We will open circuit test, and short circuit test. So why we do these things? In order to understand different loss parameters, what are different losses of the transformer, what are the efficiency of a transformer. In any electrical system, there are two kinds of losses, right? One is copper loss and iron loss, right? What are the copper loss which is occurred because of the winding and all of the transformer, called copper loss or winding loss. And another loss is iron loss is that loss which happens in the core of the transformer. Okay, I'm just giving a basics of some electrical. It's not that important, but I'm just trying, based on two tests, open circuit test and short circuit test, I can model the different parameters like resistance R0. So basically after doing some test or some standard procedures, we can make the model of the transformer. This will be something like this. Now I'm drawing the model of a circuit model of a transformer. Okay, so it will be something like this. This is input voltage V1, the primary of a transformer. Then R1 resistance is there. This is the copper. This all get from the short circuit test. This R1 model of it R1. This is L1. Now I have primary winding. Again I am show R0 and L0. This shows the iron losses in the transformer. Iron loss of the transformer. Okay. Now we have the winding of a transformer. Okay, this is R0, this is L0. Okay, and now we have a core. This is a core. Now we have the secondary winding. Now we have the inductor L2. This is L2. We have R2, and here we have load. So load is just output of a transistor. It may be connected to. It can be connected to anything. It can be connected to another device, or it can connect it to any other buses or any other channels or feeders, whatever, right? So this is R2. So this is the equivalent circuit of a transistor which we are trying to analyze. Okay, here we should know that yeah, this is the primary voltage V, this is secondary voltage Vs, whatever. Okay, so what you have done, we are trying to model the transformer using resistance, inductors, etc. based on some test, short circuit test, open circuit test, which give me these values of R0, R1 and R2 and L0, L1 and L2, etc. Right? So now how to analyze this? Now we have different circuit analysis concepts can be applied here. Right? We can use the Kirchhoff voltage law. We can apply Kirchhoff current law. For example, here the current is I0. This is the current in the core of a transformer, right? And this is I1. This is the current which is in a power, like it is power transfer net transformer, right? Primary to secondary. This is going to the winding, and I0 is a loss. I0 is loss which we cannot, which we don't need much because it is going through the core. It is not coming in the output. Okay. Now I2 will be the secondary current, and okay, I2 will be the secondary current. Okay, so these are the different parameters when I model the transformer. Now based on the load, I can again study the different kinds of loads right now, right? Because I already modeled the circuit. So by varying the load, I know there are different kinds of loads. I can have inductive loads, capacitive load, resistive loads. I think you have remember what is called power factor, right? It's nothing but power factor is just the phase difference between the current and voltage. That's it. So I can study that also, of the power factor of the transformer. Okay, based on different kinds of load, I can vary the loads also. Okay, so basic my point is here is we are taking a device, it can be a system, which can be a transformer. We are understanding what are the internal parameters of a transformer, and we model the transformer using different uh, resistance, inductance, and winding, whatever. And then based on we'll get a model of a transformer. And based on this circuit model, we can find the equation of efficiency of the transformer. We can find the power factor of the transformer. We can find the iron losses, copper losses, etc., etc. Right? Then we can also predict what will be my output if I give a specific input. Okay, and based on this R1, L1, and all this R1, L1, all those things are specific to a transformer, right? But all the transformer will have some R1, L1, R0, L0, L2, R2, right? Values may be varying, but the model will be applying for all transformers, right? Okay, so this is one way we model. I don't go into deep, but this must be sufficient. I think this you might have learned maybe. Okay, can you hold 1 minute? Guru? Guru, sir? Right? Hello? Yes, sir. Yes, sir. Yes, sir. अच्छा सर, मैं आपको मैसेज करूँ क्या? मैं क्लास में सर, मैं अपडेट करूँ? ओके 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 ओके। Okay, so that's it. Now we have taken another example of a pendulum, right? We have taken an example of a pendulum. So if you see, my point was, if you see the basics of machines, we have studied in your first year, what is basic electrical, you have seen the transformer. You can see the transformer is modeled with this R1, L1, R0, L0 parameters, and you have equations for efficiency. Efficiency of transformer, you can write like this, based on these parameters of R0, L1, L2, etc. You can write the power factor also based on these parameters. Internal power factor, what are the uh, factors which affect the power factor of a transformer. Okay, so right now we are using analytical modeling, so we don't need the transformer. We are model the transformer using these parameters. Now we can do our research or experimentation using this theoretical model, right? Fine. Okay, now another example you have taken is a pendulum, right? Pendulum. So if you model, this is a mechanical system. So if you model the pendulum, we know there are a lot of parameters. For example, what are the parameters we might be using in the pendulum example, right? First thing is you have to model. It can be any system. We have taken example of a um, the entertainment thing. I don't know what you call it. A lot of people sitting here, and this ship is going up and down. But even if you model that thing, you need a lot of parameters. One is length of the pendulum, right? Another is mass. There's mass or weight, nothing but mg, right? And we have some angle theta. This is another important parameter, how much theta we are analyzing, how much angle the pendulum has to turn. Now when you talk of When I talk of a theta, definitely, definitely, as the pendulum is going to and forth, there will be some J, or we can say J. What is J? I think J is, I think, moment of inertia. I think, yeah, we have to calculate moment of inertia. There will be some torque, TR, torque in mechanical domain, torque, and there will be opposite torque, TF, which is balancing each other, right? So there are a lot of parameters. Even weight also we have studied initially when when you were in +1 or something. We have studied mg. The weight is mg is divided into two, right? Mg can be divided into mg sine theta here, something like this. Okay, so there are a lot of modeling in mechanical also. Then we'll write the equation tr equal to tf, right? Then then we apply the mg torque equation, mg sine theta into L, something kind of. So this kind of modeling is used, which I mean in the mechanical domain also. Okay, so without using the real system, we are trying to model using mathematical equations. Okay, so this is one example. Okay, so final model, we'll get some equations, and based on that equation, we'll study how much angle maximum I can go, how much is the torque, how much should be the capacity or the strength of the chain, etc. Okay, fine. So right now, what I'm going to discuss is we are going to again going to electrical domain, where we'll be trying to understand how to model electrical system. Okay, this is a common question asked in the competitive exam also. Model a simple system. For example, we start with a more very simple example. Say resistance. We have resistance. We have a capacitance. Right. Let's try to get an equation of this model. Let's try to understand the how to derive the transfer function of such a system. Okay, so this is R, this is C. Suppose we have input is Vi with respect to time. Right now everything is in time domain. So my output also I'm taking across the capacitor. We output with respect to time. Okay, so I can assume a current I, that is also with respect to time. Okay, so what actually we are trying to find? We are trying to find the transfer function of the system. That means the model, the relation between input and output of the system. So we have modeled this system. It may be some kind of electrical system, which I can model using a resistor and a capacitor. Okay, this resistor and capacitor, my input voltage, output voltage, and current are the main factors which I am concerned. Okay, now I'm trying to model the transfer function of this system. We know transfer function is nothing but output by input, output by input, with in terms of Laplace transform. Usually we'll take in Laplace transform, right? So we have to put in S domain, right? So let's see. Before modeling, I can think whether should I use a differential equation or Laplace equation, etc. There are a lot of options. So let's start what we know. Whatever we know, we can try to model. So in this circuit, I can start with the equations I know. I know V input with respect to time t can be written as, according to Kirchhoff law. Kirchhoff law is R into IT plus 1 by C integral IT, right? IT dt, right? This is something Kirchhoff law which I have already learned in my network analysis, right? 1 by C IT dt. This is voltage across the capacitor. Okay. Now, this is the differential equation. If you want to modeling of differential equation way, this is the first step. You write the differential equation and you can analyze it. Now, if you want to model using a transform, you can apply Laplace transform here. So how will changes? This will be like if you apply Laplace transform, what will happen? So before that, I can write the equation of the output also. Output is VOT. Differential equation. The output is 1 by C integral IT dt. Okay, same thing. Now you can just take the ratio of the output to input to get the transfer function. But having a differential equation in the numerator and denominator is not an easy thing to deal with. So better we always go for Laplace transform, right? So here, if we apply Laplace transform, what happens? We can get this guy here, V output sorry, V input, Laplace transform, we can write like this. This is same is plus 1 by C it dt. So 1 by Cs, integration, the S will be in the denominator, right? Is, right? And what about the V out? Second equation will be coming like this: VOS equal to 1 by Cs Is, right? Now transfer function is nothing but, now we can write the transfer function output by input. What is output by input? Output is 1 by Cs Is divided by R into Is plus 1 by Cs into Is, right? I is the common, we can take it as a common so that it will be cutting each other. I is common in all this numerator and denominator. Okay, so now what happens? Now the transfer function becomes 1 by Cs divided by R plus 1 by Cs. I can simplify it. Yes, I can simplify it. I can simplify it by, this is Cs will be common denominator here, and here this will be cutting together. So this will be 1 divided by RCS plus 1. Okay, so this is the transfer function. So what have we achieved? What have we achieved? We achieved that we had tried to model with a digital system, electrical system, which is I'm drawing in top left, and I have tried to draw the circuit model of that system, whatever the device, with the resistance and capacitance, all those things. And from this resistance capacitance, I have written the differential equation, and this differential equation I have converted into a Laplace transform, and from the Laplace transform, I draw the transfer function, and from the transfer function, I got a simple equation of the transfer input output by input, right? So now what I have done, I have converted just okay. Now whatever the device I have, I had the circuit model of the device, and from this I divide the transfer function 1 by RCS plus 1, right? This is the transfer function. Now from this transfer function I can give my input and see what is the output. Different kinds of input I can give: step input, ramp input, whatever. So this is, now how I can say this is my model of this device, the transfer function. Okay, so this is our, now whatever input and output I can analyze using here. Okay, so right now there will be a lot of circuits. We should try to draw the Laplace transform of those transfer function, derive the transfer function of those circuits. Okay, so I'll give you another, I want you to try. I think I will one more question I will try, then you can try on yourself. There is a input, there is a resistant, inductor, and capacitance. I think this we had tried once. The output, this is C, this is L, this is R, say this is VI. Okay, so we know how to draw the differential equation easily. I think we had tried that. Now we'll try directly write the transfer function of this thing. We input S, we can assume a current I, right? So is into R, plus we know an inductor, we know we have seen differential equation. What is the inductor? L di by dt, right? L di by dt is the inductor. So in differential terms, it is L into S, right? Differential L into S into Is, right? I think you remember. I just told you to refresh your Laplace transform. Okay, then plus, then 1 by Cs. Integration means S is in denominator into Is, right? Now okay, now we have to write the equation of output also. V output is nothing but 1 by Cs into Is, that is the current into impedance of the capacitance, Is Xc. Okay, so 1 by Cs. Now we have to take the V out plus VO divided by Vi to get the transfer function. So VO divided by VI, what I'll get? This is S, both are S because transfer function I'm dealing with. So, what I'll get 1 by CS divided by R plus LS plus 1 by CS. So try to, so this is the answer. So try to simplify this. Okay, this is 1 by CS. Okay, try to simplify it. You may get something like, CS is 1 divided by RCS plus LCS square plus 1, something like this. Okay, you check it whether it is fine, then you go ahead. So this is my transfer function model, right? Transfer function model of this a device or system which I don't know, whose simple representation using RNLC is this thing. Which one? This is my simple representation of that system. It can be any system, maybe something like this star. I'm just representing using RLNC. Now what I've done, I derived the transfer function of that system. Now it's easier to analyze. This is the analytical way, right? Deriving algebra using algebra and RNLNC models and using Kirchhoff law, etc. and Laplace transform, deriving a transfer function. Okay. Now I'll draw a circuit. I request you to find the solution for that, and we will try. So I'm just drawing circuit. So now let me draw capacitance. Capacitance. Let me put a resistance parallel. Resistance in series. This is R2. This is R1. This is C. Okay. Now where I'm taking output is I'm taking output from here across the resistance, and input definitely I am giving across this terminal. Okay. So you can assume that I'm in this circuit. You can assume a current. You can see. You can assume a current I1T or IT, whatever, in this whole thing. Right. So what do you want to find? You need to find the relation between transfer function of this thing. You need to find transfer function. Try this. I'll give you maybe 4 minutes. Please try this. So you know how to do it. You know to write the equations in differential equations, or you can directly convert into transfer functions. And based on that, you need to find V out by VI. Okay, a transfer function based on frequency domain or S domain. Please try this. Okay, so have you tried this? So first we can see that, did anyone get the transfer function? Okay, so first you can see one thing. There's a current passing through this capacitance also. There's a current passing through this resistance also. Okay, basically we want to see this connection. This is parallel. This capacitor and resistance are connected in parallel, right? When we know that when two uh, parameters or two components are connected in parallel, impedance get decreased. So one way of doing this is we can find the collective impedance. We can say the impedance of this impedance, and this impedance is collective of this capacitance and resistance, and there's a resistance in the output, right? This is VO, this is VI. We can consider this is the most easiest way. Okay, because anyway we are trying to find the Laplace transform. So we know the resistance, how it will act. It will be 1 by Cs. 1 by Cs will be the impedance in the Laplace domain or the frequency domain, right? Resistance, definitely it will be R only, because there is no integration or differentiation in Laplace domains. So, so how is the parallel combination of resistance capacitance? So this is Z, something we can write. So Z here will be parallel combination of this resistance and capacitance impedance. That means R into 1 by Cs divided plus R plus 1 by Cs. R into 1 by Cs, R plus 1 by Cs. So what will be the answer? This will be R in the numerator, Cs will come here. This cancels. So R divided by RCS, Cs plus 1. Okay, so what I have done, I try to model the parallel combination of capacitance and resistance into a single impedance. And whose transfer function I got? This thing, R divided by Z. This is Z equal to R divided by RCS plus 1, right? And we have another resistance R2, across which I'm taking my output, right? So how can I write now? Okay, this is my question. Okay, this is R2, R1, C. This is Vi and V output. Okay, right now I can write V output. V output is there, V input is there. So we have converted the circuit into a simplified form, combining this impedance into 1 and R2, right? This is a parallel combination of R and C, and this is V out. Okay, from this equation we can easily write the Kirchhoff equation of this thing. That means this is R2. Okay, so can I write V out in terms of Vi from this? I can write V out equal to V input into R2 divided by R2 plus Z, right? R2 plus Z. Okay, so how can I write this? So I can take the V out into the LHS, then I'll get the transfer function, right? You can see here, here we can see V out is there, Vi is there. Now what we want is V out by V in, right? So what will becomes, we'll get R2 divided by R2 plus z. This is the transfer function. And what it becomes, right? This is nothing but R2 divided by R2 plus what is Z? We already calculated Z. R1 divided by R1 CS plus 1, right? So this is, so if I take the LCM and everything, this will be R1 R2 CS, this will go to the numerator, right? Plus R2 divided by R1 R2 CS R1 R2 CS plus R2 plus R1, something like this. Is it correct? You just check the algebra. Maybe there is some wrong, which are just where I'm simplified. Okay, so this is going here. This has to be multiplied by here. So it will be R1 R2 CS plus R2 plus R1. Okay, then this will be coming into the numerator. Okay, I think this is the answer. R1 R2 R1 CS plus 1. Okay, please check it. Okay, this type of exams can be asked in the competitive exams, in GATE and all those things. You'll be given a circuit and you have to find the Laplace transform. I think we'll stop with this question here. You just write down the answer and question if you are not written anything. If you written anything, you just continue, you'll get the answer. Now I'm changing the circuit. A new circuit will try now this circuit. We'll try. Okay. V input, V output. So this is C, this is L, this is R. Now you have to find the transfer function of this model. Now here we have already modeled a electrical system and given before you, right? It can be any device. Now have this circuit model of that device. Now you have to draw the transfer function of that from the circuits. So here also we can see there's a parallel combination of impedances R and C. So when current is passing through the capacitance, I know its impedance, net impedance can be written as 1 by CS, and inductor, it is Ls in Laplace domain, L into S. Why L? I think you getting why L into S. L di by dt. Voltage is L di by dt, right? L di by dt. So in Laplace, it will be L into S into I. Laplace, right? And integral I dt. In capacitance, voltage across a capacitance, integral I 1 by C, integral I dt. That is nothing but 1 by CS into IS, right? Voltage across capacitance. And voltage of inductor is L into di by dt. That is nothing but L into S into IS, right? So this is we are doing here. So here we are only taking these two things, 1 by CS in Laplace domain, for shortcuts, for fasting, for doing it faster. Okay, so we are just taking those things which decides my impedance L into based on S domain. Okay, so I use Ls for the inductor and CS for the capacitor. Then what happens? Okay, then I can write this is parallel combination. This is equivalent circuit is a Z impedance and a resistance. This can be R. So what is this Z? Z I know is a parallel combination of this thing. That is nothing but 1 by CS into Ls divided by 1 by CS plus Ls. Okay, can simplify it if you want. You may get something better here, 1 by CS, or denote cut that thing. Okay, you can see it. You can get something here for Z. Now what is V out in terms of V in? You know, V out equal to V in into R divided by R plus Z. R divided by R plus Z. right? So what happens? So r divided by r plus z, we know r is symbol r divided by r plus, this whole thing comes here, right? The whole things comes here, and you can simplify it. Okay, so things are not difficult. It is easy, but you just need to see the algebra. So we are trying to derive the transfer function. Okay, so can anyone tell me the answer for this? Okay, I'm getting answer. Let me try also. Because let me verify also the answer. So this is r divided by r plus this thing. If this is simplified, it will be LC square ls divided by 1 plus LCS square, right? So if I take this again, if I simplify this, so r into 1 plus LCS square divided by r into 1 plus LCS square plus LS, something like this. Yeah, 1 plus LCS square divided by LS plus r and 1 plus LCS square. Yeah, fine. Okay, so this is what you get. So you should practice something. I'll get one more final question, so we can do this thing. So I'm giving question like R1. So you can try this, right? This is V output. This is V input. This is R1. This is R2. Or yeah, you can try this R1, R2. So while just seeing this question, we should know we are directly getting input and output directly. It's a voltage divider, right? So the equivalent circuit should be something like this. We have a resistance and impedance, because it is a parallel combination of resistance and a capacitance. Here I am not given the name of the capacitor, let it be C. This is C, capacitance. Okay, so this I can represent using this. This is the resistance R1. This is nothing but R2 parallel C, where I'm taking the output. Okay, so if I see the Laplace thing, 1 by Cs, this is 1 by Cs, and this is R2 only, and this is R2 only. So I can write V input equal, sorry, V output equal to V input into 1 by Cs parallel R into R2. R2 divided by R2 plus 1 by Cs, right? Divide by R1 plus the same thing. Same thing in the numerator will come here. Same thing. The same thing will come here. So what will be the answer? So the transfer function is nothing but V output by V in. It's nothing but when this guy comes here, LHS as a denominator. So we'll call the transfer function. Okay, so can anyone give me the answer? Okay, so it is like, you can try this is algebra, but don't make mistake. Yeah, so one is already written. Okay, so don't make mistake, that's the only thing. So let me try 1 by r2 here by cs. So this is r2 divided by r2 cs plus 1, right? This is the parallel combination. Divide by r1 plus the same thing, r2 divided by r2 cs plus 1, right? So this is the answer. You simplify it, we can see that this will be taken common. So this guy will come here, and denominator both will get cancelled, and you may get, I think this kind of question is asked in GATE also. You'll get given the some circuit, you have to draw in fast. So this thing very helpful. Get directly converting into Laplace transform and just do fast. So this will be like this r2, and this guy will go denominator, r2 cs plus 1. This will be in the numerator. Denominator I will have r1 r2 cs plus 1 plus r2. This is the answer. Okay, but in GATE the solution usually will be in the second domain, second order. It will be simplified, fully simplified. You have to multiply into cross multiply, and you'll get the final solution. Maybe, usually, or you have to multiply, cross multiply here. That's it. Okay, so this is the solution. So I think now I'll give you one more question. Say one question is like this. Okay, now I'm giving a question. Now we already done this circuit, right? With a resistance and a capacitance. I think we have done this circuit in the first question. We have done this thing, right? Suppose 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 I have one more branch like this. Suppose I have one more branch like this. What will happen? This is R1, this is R2, this is C1, this is C2. And this definitely we have input output Vi, and V output across this C. How it will work? Now you should remember there are two resistance and two capacitance, C1, C2, R1, R2. R1, R2 are different, C1, C2 are also different. And some rare, and some usually, I think you have seen the Wien oscillator, some kind of oscillator, Wien bridge oscillator kind of circuits in Wien bridges. So where both R and C are same usually sometimes. But here, first you should derive an equation of transfer function with, can say R1 equal to R1 and R2 are different, C1 and C2 are different. Then there may be a special case when both resistances are same and both capacitance are same. Then you can get a simplified equation. So this is one thing you can try. So this is so there's a one question, because last transfer function with only this whole block, I got a transfer function like this. You imagine, sorry, you got the transfer. If you see in your notebook, you got a transfer function like this: 1 divided by 1 plus RCS, right? In this case, it will be R1 C1S, right? So this is one block, right? So what I'm doing, I'm just connecting another block in series. So is it like this? I'm keeping another block like this, whose transfer function is 1 divided by 1 plus R2 C2S. Is it like that? I think you want to. I want you to think. So it is like what? This is gain G1. This is gain G2. So net gain is G1 into G2, right? So does it mean that I can multiply this to transfer function, or is there any problem here? So I think you can see this. You can see this because this is especially sometimes in competitive exam they'll ask like this, some circuit like this. This again this is called Wien bridge oscillator kind of thing, because if you know one transfer function of one among them, can you multiply this into this into this, and we'll get the overall transfer function as we are doing in block diagram reduction. So that is a question. I think you can explore it. First, you try what is the transfer function of G1 into G2. So you'll get something like this. If you multiply it, I'll get something like this now. 1 plus R1 C1S into 1 plus R2 C2S. Right? If you multiply these two things, G1 into G2 here. But now you try this separately and find V output by V input. Then you will get something different. Let's see, you just see, and if you're getting different, that means this techniques won't work. If it won't work, why it won't work? If it work, why it works? Okay, so please try this and we will discuss. And also try one more thing. Try this and then try one more thing. Also try one more thing. I'm just changing. I just take a snap of this. It'll be better for tomorrow. Okay, also try one more question. This is also another important question, competitive exam point of view. It's the capacitance resistance. Just interchange capacitance resistance. Okay, then as usual we are giving input Vi and we are getting output V output across the resistance, right? So we can assume here all the capacitance are C, R. Here also the questions remain the same. What is the transfer function? Or you can initially you can calculate R1, R2, R3, C1, C2, C3 and find the transfer function, right? Then what the special case? You can take a special case after that. C1 equal to C2 equal to C3. You can take it as C. And similarly, R1 equal to R2 equal to R3 equal to single R. This is a special case. Okay. So here also the question is, if I know the transfer function of this thing, can I multiply it or take a cube of that? So what will be the transfer function of that thing? So this thing, my transfer function will be 1 by Cs. This is R divided by R plus 1 by Cs, right? This is nothing but RCS divided by 1 plus RCS, right? So if I have the transfer function of that thing, can I cube? Can I take a cube of those three transfer function in series? So I can do this cube to get the overall transfer function of this circuit. Is it possible or not? This also you have to see. And if it is not possible, you have to tell why it is not possible. Why is not able to multiply it. So what is makes it uh, difficult to apply that thing? Okay, so these two questions you can try it, kind of small research kind of thing. So again, try this. Okay, and also put this special case after you derive the expression of the transfer function in terms of R1, R2, R3, C1, C2, C3. Then take this special case. I think this is a phase shift oscillator kind of phase shift oscillator. Phase shift oscillator, this phase shifting circuit. I think you have learned in your analog circuits this thing. I'm not sure. Okay, okay. I think that all from my side. If you have any doubts, you can ask. Okay, so if you have no doubts, you can put your roll number and also tell me